It's good for you. It's a vitamin.
All right, hi everyone. Let's get started. So welcome back. Today we're going to be talking about advanced UV architectures. And before we do that, some announcements. Mainly that homework 1 is due tonight. Don't forget to submit it, and please include your model predictions on the grade scope. As kind of a temperature check, how is everyone doing on homework 1? What's wrong?
I submitted it. I got the points. It's just for the I need to go to office hours, but I have midterm, so I haven't had the time.
Sounds good.
But I wanted to like sit down with somebody from the club and like talk about how to optimize the thing because I just like.
Sounds good. Yeah, absolutely. Feel free to come to office hours and like email us or that's time. Yeah, wonderful. Yeah, so for outline, today we're going to be talking about, first of all, just a review of convolutions and kind of just like what the structure of a CNN is. Then we'll dive into the models we're going to be talking about. So this will be kind of a review of 2012 to about 2017 or so. And then we'll finish off with the conclusions. Yeah, so to review CNNs, starting off with history, as you've probably seen the slide before, in 1990s, we had a breakthrough of LUNET 5. Jan LeCun came out with the architecture, proved that you can recognize digits, but it was very small, very slow. And it wasn't until about 2012 that AlexNet came out. We realized we can use GPUs to train CNNs, and it was a massive breakthrough. And then after 2012, we've kind of just had an explosion of computer vision networks. So this shows kind of like major models up until about 2019, 2018, and we've had more since then as well. Yeah, so yeah, original architecture proposed in the 1990s. AlexNet, groundbreaking, like, whoa, we can use GPUs to train. And since then, everyone was basically like using the same GPU framework. So I guess the frameworks evolved, but everyone was like training on GPUs now. Bigger models, bigger GPUs, and so on. And then again, to refresh the structure of a CNN, we kind of have a convolutional backbone, which is just composed of convolutional layers, activations, and maybe pooling layers stacked together. This is what we call like the feature learning, the featureizer of the backbone. We flatten everything, and then we put it into a classification head. And the classification head is typically composed of just fully connected layers, as you've learned in like the first couple lectures. In this lecture, we'll still be talking about classification. Future lectures talk about how do we expand to object detection and so on. So diving straight into it, AlexNet is the first model we're going to be talking about, 2012. Take a look at it, maybe turn to your partner, discuss some things kind of like that you can observe about it and kind of like what stands out here. And then as well to kind of just like give some intuition, kind of like how do we read this diagram. These are basically convolution layers. So there's like one convolution layer of kernel size 11 by 11. We have a pooling layer, convolution, pooling, convolution, convolution, convolution. We flatten everything, and then it goes into 2 or 3 fully connected layers. Yeah, so just, I guess, yeah, turn to your partner, talk just a little bit about like what you see. So I guess, yeah, do you guys have like observations, anything you want to like, anything you notice about this that's interesting to you? So all right, let's come back here. Any questions about this, first of all? Any comments? Yeah.
So in this diagram, right, like after the first convolution, it looks like there's some crossing behavior happening. Right?
Yeah, so that's mainly for A, visualization purposes, and B, because GPUs in 2012 were very small, what they actually ended up doing is breaking up the model into 2 GPUs to be able to train it. So in convolutions, it's kind of like hard to understand this, but in fully connected layers, you see that there's two layers of like in stuck together of 2048 by 2048, and they're crossed over and kind of fully connected as well. And the reason they did it is because they couldn't fit a 4096 by 4096 layer into a single GPU, so they had to break it up into two to be able to actually train this model. So I guess going into like observations, first of all, it's very shallow. There's only, as you can see, like 5 convolution layers. So our featurizer is not very deep at all. Second thing is the dense layers are very hefty, right? As you notice, like we had to break it up into 2 GPUs. And the reason is because we have 60 million parameters just in those fully connected layers for the classification head. So you kind of have our flattened latent of 13 by 13 by 128, going into a layer of 4096, another layer of 4096, and then going into 1,000 class classification. So 60 million parameters. And this is especially large compared to like 3.5 to 4 million parameters that we use for the featurizer. So the featurizer in AlexNet basically doesn't cross that much. Most of the compute is still done by the classification head. So what are some things you want, kind of like based off of these observations, what do you want to change to like create a better architecture? Yeah. Exactly. So we want to decrease the number of parameters in the classification head to make it lighter. What else? Yeah.
Maybe just like, I don't know if that's in pursuit of what you were saying, but can we create some of these dense layers for convolutions?
Yeah. Yeah, exactly. So we want a deeper network. We want kind of a more capable featurizer. Yeah. So as you will see, kind of as the theme with most of these networks that we're going to cover is just, first of all, go deeper. The idea is more convolutions means more abstraction, means that the network is able to learn more complicated features. And then also you want to get around the dense layers. They're taking up lots of space, slowing down the model training, the model inference, and just everything. And the solution that addresses some of it is VGG. So I think it was like Visual Graphics Group in England came out in 2014 with VGG. And so take a look at this network. Each of the layers, so kind of, it was the input image, and you have 2 convolutional layers, you have a pooling layer, 2 convolutional layers, a pooling, 3 convolution, pooling, 3 convolutional layers, pooling, and so on. Yeah, so I guess let's do the same exercise, just like turn to apart and talk to each other, like see what you observe here, like what does this, how is this model better or worse, and so on. And feel free to ask any questions that you have. So first of all, how many convolutional layers do you see in this network? Answer is a lot more. You don't have to count exactly. Yeah, so I think 23 or this particular visualization might be like around 15 convolutional layers. 1, 2.
So they have more convolution layers that drops in the group parameters. Just focus on a few specifics.
So I don't think they actually dropped any number of dense layers. So the linear kind of the classification head is still the same. I think there's 2 4096 by 4096 blocks. Not too clear perhaps in this visualization, but they kept the classification head. What they basically did is, first of all, they made the network a lot deeper by just adding convolutions. So the idea is like the featurizer is going to be more capable. And second of all, they introduced some kind of structure, some kind of sense into this diagram. And the way you see it is just like you have a couple conv value blocks followed by pooling, couple conv value blocks followed by pool, couple conv value blocks followed by pool. And at each of these steps, they increase the number of channels by 2. So they decrease height and width by a factor of 2, and then they increase the depth by a factor of 2 as well. So you can see kind of like the first kind of featurizer kind of extraction has 64 channels. Then after the first pooling, it goes up to 128 channels. After the second pooling, it goes up to 256 channels, and so on, up to 512. And then for computational efficiency, or perhaps it wasn't necessary, they didn't go up to like 1024. But that's kind of the structure they followed. So this kind of general structure kind of help to shape future networks as well. Just kind of like the idea of like you're going to gradually decrease the number of, or the height and width, and double the depth of our blocks. Yeah.
Did that have a significantly larger, I'm assuming it has a significantly larger hardware requirement too?
Absolutely. But in 2014, it was less bad because people started focusing kind of like AI hardware and NVIDIA came along. And so it was massive. So 138 million parameters or like taking up 500 megabytes of storage. So training it was definitely difficult, but it was less of an issue because more capable GPUs came out by that time. So it was okay, but VGG is still kind of like a huge network that is unnecessarily large for kind of how good it is for most cases. But yeah, it's a lot deeper. VGG 19, I think, has 23 convolutional layers. We still have the 3 hefty dense layers, so we did not get around those at all. But yeah, and the other important thing is like repetition of standardized blocks. What you will see in the development of future models is we develop kind of a standardized block of compute and kind of like a block of like a featureizer. And the way we build like smaller or larger models typically is just by like adjusting the number of blocks that we use. Yeah.
So why would the number of filters increase?
Yeah, it's because you have as you get kind of like deeper, you start learning more high-level features, and there's a higher variety of like high-level features that you can learn. So if you think about it, like at a low level, like in the first kind of couple of stages of a featureizer, you're learning about kind of like edges in different orientations or peaks or like small textures. As you get deeper, you're beginning to learn features such as like arms or wheels or hands, faces, and so on. And so there's a much larger variety of kind of like those features. And so going towards like a higher channel number as you go deeper helps a lot. At least that's kind of the intuition. In reality, the actual answer is we found that it works well. Yeah. Any other questions about this? Yeah. And so going forward, kind of again, the things we want are, of course, better accuracy. And so the first guess, what if we just go deeper? And the problem is going deeper doesn't work. Accuracy begins to level out, and then at a certain point, if you go to like, let's say 50 convolution layers, accuracy actually decreases. So I guess let's do the same exercise again, turn to your partner and try to like come up with some guesses of like, why does going deeper decrease the accuracy of our models? If you guys have guesses, feel free to raise your arms. Yeah. Overfitting could be one, yeah. Yeah, as you get more parameters, you're able to fit your data set better. But in this case, kind of with a large data set like ImageNet, we're still definitely not overfitting to it. We're just actually like learning a lot worse. Like even our training accuracy decreases as well. Yeah. Dimension of the image, or do you mean like kind of the tensor in the middle of the features? Well, we don't have to necessarily like decrease it. Like, for example, perhaps we can stop halving like the height and width and like, get rid of pooling layers at the end and just like keep doing more convolution stuff. If we just like stack 50 more convolutions at the end of VGG, it does not get better. Kind of like one. Any guesses from like this side of the room? Yeah. Right. The root cause, I'll kind of give it away, is actually vanishing gradients. And so the way to think about it is, let's say we have like 50 convolutions stacked together. As we backpropagate all the way from the loss, which is at the very end of our network, all the way up to the beginning of our network, our gradients become very, very small. Because in the backpropagation algorithm, to compute the gradient of like layer n, you use the gradient of layer n plus 1. And as we do that and as we go deeper and deeper, you realize all of these gradients kind of multiply together and they become very, very small. And so vanishing gradients are the reason kind of like VGG cannot go like any deeper. And the reason like VGG is kind of like the limit of traditional convolutional architecture, like the simple one. And the solution we came up with at first was very complicated, was inception nets. And so there's a lot going on in here, so I will kind of digest it slowly. First of all, notice that there's kind of a standard building block, and we just kind of stuck it all the way down the network. And this building block, as we showed it here, is composed of convolutions of different sizes. So first convolution is going to be like a 1x1 convolution. We have a 3x3 convolution followed by a 1x1, a 5x5 convolution, and then a 3x3 max pooling followed by a 1x1 convolution. So we kind of have this branching, and then you put them all together. We'll talk about like why that's done in a second. And so InceptionNet basically just like takes the VGG block and makes it wider, more complicated, and then stacks it the same way, kind of like in line. Second thing you should notice is these kind of heads coming out of the network. They're called auxiliary heads. And so there is one right here and one right here. And if you notice, the architecture of this is like very similar to what happens at the very end of the network. And so what these are actually points where we plug in classification heads in the middle of the network to help during training. And so basically, when we compute the loss during training, we're going to compute the loss given this solution, given this solution, and given this solution. And the intuition is that as we go deeper in the network, it's going to be kind of like better. So the final kind of prediction should be the best. This prediction kind of in the middle uses like slightly lower level features, so it will be slightly worse, and then this one should be the worst. But during training, because we compute loss at all 3 points, it would encourage kind of like more gradients to flow through, and it would encourage kind of features in the middle of the network to also learn features that are relevant and not kind of just like arbitrary. So it helps address the vanishing gradient problem. A little aside for 1x1 convolutions, you learn kind of like 3x3 convolutions, take the dot product and aggregate it. What's the point of 1x1 convolution? And basically, it's the quickest way to apply a nonlinearity, and it's also the quickest way to change to increase or decrease the number of channels that we have. So what happens is kind of like all of these, like in an image, all of the kind of pixels over, like we take the sum over, or we take the weighted sum over all of the channels, we compress it, and that becomes like one feature in the output. And then depending on how many like 1x1 convolutions you have, that's going to be the number of output channels. And so you can think of it as kind of like an MLP over all of the channels dimension. Yeah, so by applying like 256 of them, we can create an array of like 256 features. And so going back to kind of like InceptionNet, some observation is that there's a lot of 1x1 convolutions. So there's a lot of places where we want to change the number of features that we have and number of like, channels that we have. And also just like being able to stack them together. It's deep and wide. And so the reason we have this branching and like coming back together is so that you're able to capture features at different scales. So as you saw, there's kind of like a 1x1 convolution, a 3x3, and a 5x5. So the goal of those is to capture features at different scales to be able to detect kind of like small and large objects in your network and so on. And then the auxiliary classifiers and losses. And kind of the explanation for it, as I mentioned, but kind of more specifically, is to expect to encourage discrimination in the lower stages of the classifier, to increase the gradient signal that gets propagated back, and to provide additional regularization. Yeah.
I understand what it is now. You know that I'm having trouble visualizing why it is and how we would implement.
Yeah, basically, kind of like in VGG, the flow of data is kind of like going through one pipe, right? But here in InceptionNet, a pipe breaks into 4. So kind of like all of these convolutions get computed like in parallel, and then we stack it back together. And so the idea is kind of like it's wide to kind of like do different operations at the same time and then stack it together. Again, to be able to like compute at different scales. Does everyone understand kind of like what wide means here? Like, does that explain it well? Yeah. Okay, wonderful. But yeah, feel free to like pause me and like ask questions. Yeah, and so based on this, some things you want, of course, as always, you want better accuracy. We never stop like looking for the next best network. But also you want a simpler architecture. this was a mess to look at. There's like deep, wide, there's all sorts of like different convolution sizes and so on. So ideally, we were able to achieve the same thing, but not having such a complicated architecture that might be like very difficult to use. And the solution was ResNet. With ResNet, we're not going to look at the architecture right away. We're going to start with an intuition. And so going back to the vanishing gradient problem, let's say we have a training network. Adding more layers to it, just adding, let's say, more convolutions should not hurt intuition, because they should be able to just learn the identity transfer, right? And so the accuracy should at least remain constant. And again, to remind you all, the thing we found in VGG is that adding more layers actually hurts the accuracy at a certain point. And so this kind of like breaks this intuition, so our hypothesis is incorrect. And the reason is, the hypothesis doesn't hold up. Again, the reason is vanishing gradients, but I guess another intuitive way to look at it is the identity is actually surprisingly difficult to learn. The reason is because it's like the identity matrix is very specific, and to be able to set like all of the values to near zeros and like set the diagonal to 1, it turns out it's actually like difficult to learn that. And so the way ResNet proposes to address this is just make the identity easier to learn. And so it came up with this. So what's happening here is that we have X, or our previous tensor, like an image coming in. It's going through like weight layers. So in this case, it could be convolutions, but it could also be just a linear layer or another type of layer. Go through one of them, go through rarely, go through another one. And then what you also have is a skip connection. And so the skip connection is going to skip those two layers, and then we're going to just add them. And so after these two layers, we're not going to have just f of x, we're going to have f of x plus x. And now to be able to learn the identity, we don't need to actually learn the identity matrix, we just need to learn the zero matrix. And the zero matrix is very easy to learn because we can just use backpropagation to set everything to 0. And neural networks and backpropagation is very good as well. Does everyone see kind of like why this makes identity easier to learn?
You're keeping the original signals.
Exactly. You're keeping the original signal, you're propagating it through and adding it to the featured signal. And this is what kind of ResNet 34 is. So on the top, we have ResNet 34 with residual connection. So like every 2 layers will have a skip connection, every 2 layers will have a skip connection, and so on. And then at the end, we're going to do global average pooling, which we'll talk about. And then we're going to have just one fully connected layer. In the middle, we have a 34-layer neural network, but without skip connections. And then at the bottom, we have VGG19. So we can see kind of like even a baseline ResNet. 34 is like a fairly shallow ResNet that went up to like 150 or like 200 layers or something. It's already like a lot deeper than VG. And what we found is that adding skip connections makes identity easy to learn. It also makes our loss surface nicer, as well as like patch normal. And so there was a paper that kind of visualized loss landscapes of neural networks, and they were able to like confirm that the ResNet's loss surface looks a lot smoother, and which makes backpropagation a lot like more effective on neural networks and makes kind of makes it easier to learn a more optimal solution, like makes training a lot more stable as well. Some observations about the network. First of all, it's long. It uses global average pooling. So global means averaging over each feature map over like the height and width dimensions instead of the channel dimension. And so, for example, like a 7x7 by 512 block would get averaged down to like a 1x1 by 512 block. And what this does is it forces last feature maps to be more closely related to the actual classification categories. By not having kind of more linear layers after it, our convolutional featureizer is going to learn actually like relevant features. Linear combinations of feature maps become category confidence maps, which you can actually visualize. And the robustness to this also makes the network robust to spatial transformations. If feature is present anywhere in the network, it's going to get picked up in the average pool. And this also means we cannot train on different resolutions of images if we want. let's say we feed a 512 by 512 image, it's going to get down, let's say, to like 4 by 4 by 512 features. So global average pooling is going to like average it down to 1 by 1 by 512. If you feed an image that's like 1024 by 1024, so twice as big, it's just going to be an 8 by 8 by 512 feature map at the end. The global average pool, it still becomes 1 by 1 by 512. So our network becomes agnostic to image resolution. It just needs to be like a factor of 32 or something, or like depending on the network. But it can be like as large as we want. The input image can be as large as we want. And then, yeah, only one fully connected layer at the end. So we finally solved this problem of like a huge classification head that makes our network very slow. At this point, basically all of our parameters are going to be in the featurizer. Yeah, any questions about ResNet? Wonderful. Yeah, so global average pooling, a bit more about it. It's designed to replace like the fully connected layers in the CNN, the huge classification head. Yeah, I'm gonna mention all of this. Yeah, and global average pooling doesn't have any parameters in it, so we're less prone to overfitting versus with a fully connected layer. Just because there's so many connections, we can be prone to overfitting. Yeah, and so things we want, of course, faster, smaller, and better. And the solution we came up with was mobile nets in 2017. And the way they approached it is they wanted to reduce the number of parameters in the network. So they were looking at convolutions, figuring out what can we do to like keep the same kind of level of featurization, but do like basically the same operation, but reduce the number of parameters. And so the intuition was, as we get deeper, the number of channels can get pretty large, right? As we've seen, like even in VGG, we go up to like 512 channels. And this is what leads to a lot of parameters. And the questions they asked is, what if we process each channel separately? Are we still going to be able to like learn from all the data? And is this going to be more parameter efficient? And the solution was depth-wise separable convolutions. So first off, let's talk about depth-wise convolutions. So on the left, you have a normal convolution. You have an RGB image, you have a 3 by 3 by 3 convolution kernel, and that's going to become 1 pixel in the output feature. With the depth-wise separable convolution, with the depth-wise convolution, instead of kind of summing over all the channels, we're going to skip summing all over the channels, and each kernel is going to produce 3 outputs in the output feature map. And so we have a 3 by 3 convolution, and it's going to produce 3 pixels in the output feature, in the output like activated map. So after a depth-wise convolution, our channel dimension does not change. Does this make sense? We just basically do not sum over the channel dimension. And then after that, we just add a 1 by 1 convolution to have as many activation maps as possible. And so this depth-wise separable convolution is going to essentially kind of do the same thing as a regular convolution, but it's going to have fewer parameters, and it's going to be a lot simpler. And so let's do kind of a small example. Let's say how many parameters does a normal convolution have versus depth-wise convolution? And then in this example, let's say we have 3 input channels, so an RGB image, we have a 3 by 3 kernel, and we have 8 output channels with no bias. Yeah, why don't you guys like turn to your partner and like try to calculate this? And so as a quick reminder, also like in a depth-wise separable convolution, we're going to have like a 1 3 by 3 by 3 block, and then we're going to have 1 by 1 convolutions for as many output channels as we want. You don't have to calculate the exact number, you just have to like say how to calculate it. Anyone who guesses? $24. I don't actually remember. I think might be. How'd you get it? Yep. So that's going to be for the 1x1 block, and then what else? Yeah. Oh, do you have nothing?
Yeah, and then you need to, sorry, yeah, and then you need to have the kernels that flies in front of it.
Yep. Exactly. So for a normal convolution, we're going to have just a 3x3x3x8 because you have a 3x3x3 block for every single output channel. So there's going to be like 216 parameters. And then for the depth-wise separable, as you guys mentioned, there's going to be 3x3x3. So for the kind of like depth-wise block, plus the 3x8 portion, which is going to be like 24 parameters for the 1x1, like the second half, the separable portion. Does everyone understand how we arrived at this calculation for both the normal convolution and the depth-wise separable convolution? And does everyone understand the CKHW notation as well? Yeah. No, because remember in convolutions, you can have slide over the image. It doesn't matter what the height and width are. It only matters like the number of input we have. The size of the image affects our computational cost, like how many times we have to slide over the image and like how big our loop is and like how many times we have to like go through the image, but it doesn't affect how many parameters you have. Yeah. Wonderful. If there are no questions about this, kind of some observations about kind of MobileNet. You have the architecture on the right. It's kind of like just a mess to read, but basically it's like a bunch of depth-wise separable convolutions. It's simply alternates kind of like regular and depth-wise separable convolution blocks because kind of like fully like normal convolutions still do learn a bit like more parameters. They have more parameters and they do learn a bit more. And they found that like alternating the two types works well. They have reduced the parameter count quite a bit. So if we look at the previous example, just for like this small example of like a 3-channel image and like an 8-channel output, we're already at like 4x parameters fewer for a depth-wise separable convolution. Most of the multiplication adds happen in the 1x1 columns. So that's kind of like a consideration when we optimize the model. And what ended up happening is it ended up matching the inception with 3 accuracy. It was like nearly 10 times fewer parameters and a 10x speed up. And so this was a very impressive architecture that probably still runs on a lot of you guys' phones. That's why it's called MobileNet. It's like we're trying to reduce the network down to a size that can actually run on phones. Yeah, and you can see kind of when they change the network from regular convolutions to depth-wise separable convolutions, they reduce the number of multiplier adds by a factor of 9, and the number of parameters also by like a factor of 9 or 10. And so that made the network a lot lighter, a lot faster, while being able to preserve accuracy fairly well. Wonderful. And so some takeaways in terms of core concepts. First of all the models we design are going to be trade-offs between accuracy, performance, and model size. Like even if you look at Inception V3 and like MobileNet, there was some trade-off in performance and model size, right? If you want to make the model smaller and more performant, we might trade off accuracy a little bit and vice versa. Good design of convolutional neural networks generally follows a slow decrease in the height and width and a slow increase in the number of channels. So that's what kind of like AlexNet came up with, and then VGG kind of confirmed with like a deeper network. Papers like EfficientNet and RegNet, which are primarily kind of like architecture tuning papers, found this to be the case for CNNs. So for context, they did neural architecture search, and the computer kind of like verified that this works well. RegNet from Facebook research is actually a very readable paper that does architecture search. So I recommend you guys to read it as well. And lastly, hyperparameter search is used for squeezing maximum performance. So these are kind of hand-tuned networks that we found. Nowadays, a lot of the networks we use were kind of done through neural architecture search of just like huge compute centers like Facebook, Google, etc. Doing a search over like a huge set of parameters. And then some architecture building blocks that you have like should keep at the back of your mind whenever you like design architectures. First of all, is residual connections or skip connections, absolutely necessary for like training deeper networks on VGG. Inception blocks, kind of group convolutions, being able to learn at different resolutions. One-by-one convolutions for being able to resize kind of the number of output channels that you have, and kind of like learn features across different input channels. There's also separable convolutions for creating very efficient networks. Auxiliary losses for being able to train a kind of input gradient, inject gradient signals in the middle of a network. Squeeze excitation blocks, which we did not talk about, and diffused and beconf blocks that we also did not talk about, but we'll talk about in the next lecture. Here's the attendance code. Thank you guys all for coming. And if you have any questions, I'll be here for a couple of minutes.
What lecture number is this?
7.